So, we talked about working problems where you want to convert from inches to centimeters or something like that, and you use an equivalency statement, okay, to get from point A to point B. Now, I'm going to do, in this case, we're actually going to use density and mass percent as conversion factors. So they aren't like equivalency statements, but they are already a ratio. Density is a ratio of mass to volume. Weight percent is a ratio of grams of component per 100 grams of the mixture. So those are already ratios ready to be used like this, or we can flip them and use the inverse if that's what the problem calls for. So it looks kind of like this. You know what you can use, like if you have it's like a property. Density is a property of the object that it's describing. And you know what you can use it as conversion factor to go back and forth between it if you have locally units. So in you guys' lab Thursday, you came up with units of density as grams per milliliter and grams per centimeter cubed. Right there in the units are how you can use it to get back and forth between grams, between mass and volume. So we're going to work these two problems. They're kind of, straightforward problems. Problems that are both related to the same substance, methanol. So we have methanol, and the density of methanol is 0.792 grams per mil. Now, the next slide, you're going to see that 0.792 grams per mil unpacked. I should never look at a chemistry problem and see 0.792 G/ml. It should always be unpacked. And once you unpack it, you're going to have grams per milliliter, and actually we can use that as conversion factor. In the first case, we're going to go from the milliliters. That's going to be our first term. Notice I focus on the units. I don't care if it's 242 milliliters. It's a lot of milliliters, okay? So we're going to put milliliters as our first term. They're going to use density to get from milliliters to grams. That's it. The next one is, notice we have grams. We're going to start with grams. We're going to use density to get to milliliters. So it looks like this then. Oh, this is the unpacking. So again, think of 0.792 grams per milliliter as a property of methanol. Do you think that property changes with temperature? Yes, it does. Very temperature dependent. Usually, I think it's like 20 degrees Celsius or what these constants are given at. Do you think there's uncertainty in 0.792? Yes, it's an approximate. So we have all these things saying this, they all say the same thing with regards to density. So to work our first problem, like I said, you're going to put your 242 milliliters over 1. That's going to be your first term. Now, in this case, I know that I want milliliters to cancel, and I'm going to be left with grams. Sometimes I'll even put the units in my conversion factor, which is not really conversion factor, it's density. But I want to put milliliters down here and grams up here. So, like, what number goes on the top next to the grams? Yeah, it's that 0.792. What number goes down here by the milliliters? Just 1, exactly. It's going to look kind of messy here, but hopefully. Yep. So that's the density. I wonder if I can you erase like this? No, that's too cool. I think you can erase like this. Oh well.
Probably open like a toolbar and select it.
There's a toolbar down here. Oh, you are good. Okay, so like this guy. Thank you. How fun. Oh, perfect. That's exactly what I wanted. Thanks. See? You could be a teacher. So milliliters cancel, and we're left with units of grams. And I've gone ahead and shown this. We have to round it according to 3 significant figures. Is there uncertainty here in the 242? There is uncertainty. Yep. There's uncertainty because it's approximately 242 milliliters. Yep, there is uncertainty. We got 3 sig figs going there, and I already told you there's uncertainty in this density, 0.792. And is there uncertainty in this one? No, that's by definition. Yep. So that's how we got our 3 sig figs. So now to work the second problem, what's going to be our first term? 50 grams over 1. Very good. Specifically with 3 sig figs. 50.0 grams over 1. Perfect. So now I want grams to cancel, so what units are going to go on the bottom?
Grams.
Grams are going to go on the bottom, yeah. So do you see in this case, we're going to use kind of what I call the flipped version of density, 1 milliliter over 0.792 grams. That's legit. Now my grams cancel, I'm left with milliliters. Showing fingers, how many sig figs? We're going, Lindsay's on the, yep, 3 sig figs. Very good. Can you see the board okay? Okay. So that's it. Now, don't make it harder than it is. Now, this is a good example. Some you guys remember when you took chemistry in high school, or maybe you don't remember. But we're definitely going to, when we, for instance, use molar mass to convert from grams to moles or moles to grams, we're definitely going to use molar mass just like we're using density here. We're going to unpack the units. So, okay, let's do another problem with regard to weight percent. Now this is where you may or may not remember this, but if you're given the weight percent, like it's a property of the sugar solution. This particular person made it up at 7.2% sucrose. It's like sounding familiar. Now you need to be able to unpack that. I'm going to do that on the next slide, but I'll go ahead and do it right here. Anytime you see percent, notice that's parts per 100. In this case, it's parts per 100 grams of the mixture. In this case, the mixture is the solution. So, in other words, and that's exact, that's by definition, that's what your percent means. So it's 7.2 grams of sucrose per 100 grams of solution. That's what I mean by unpack. I know sometimes in working story problems over the years, you've just said, well, 72%, that's like 0.072 times blah, 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 blah. We're not going to do that. You have to unpack it and use the labels that go with unpacking. It's grams of the component, in this case sucrose, over 100 grams of the mixture. All right. So in the first case, our first term is going to be, see, I go right for the number and whatever units worth the number. So our first term is going to be 65 grams of solution over 1. Then we're going to use this, and we're going to want grams of solution to cancel, so we're going to use it just like that. Okay, to get to grams of sucrose. The next one, our first term, is going to be 3.3 grams of sucrose over 1. And notice we're going to have to flip this to get grams of sucrose to cancel. That's kind of what it looks like. So this is, again, kind of unpacking that 7.2%. Now again, you're like, oh, Mrs. Strange, it's just like 7.2. I know the concept of that. I know kind of how that works in working problems. But this is how you're going to have to use it here in chemistry. And there's a reason. Actually, we're going to finish up this part with a nitric acid example where we know the weight percent and we know the density. We're going to have to do a problem. All right, so to work the first one, So notice weight percent. Weight percent is grams of component over 100 grams, also grams, except like grams of mixture or solution. The word is explicit, so you have to be explicit, give a lot of information about those grams. You can't just say grams and grams because you're like, oh, grams of what, oh, grams of what. Okay, So no pun intended, the solution to this problem. So in this first case, we were going from grams of solution to grams of sucrose. So we're going to put that 65 grams of solution over 1. So if we want units of grams of solution to cancel, what units are in the denominator of the next term? Grams of solution, yes, exactly. And when we unpacked weight percent, we had, by definition, 7.2 grams of sucrose per 100 grams of solution. And again, just to make sure we're all on the same page, when I do this on my answer keys, I would put the first term over 1. So we're done. We have the units we want to be left with, which is the way factor label process works. So show of fingers, how many sig figs do you guys think we need to allow in our answer? I'm seeing 2-ish, that's right. Very good. So 4.7 grams of the component, 4.7 grams of sucrose. So for the next one, our first term is going to be the mass of solution, the mass of sucrose, 3.3 grams of sucrose. So if we want grams of sucrose to cancel, what units need to go in the denominator of the next term? Grams of sucrose. So you see where we have to, I call it kind of the flipped version of the weight percent. So in this case now, we put 100 grams of solution over 7.2 grams of sucrose. It's all about the units, baby. Okay, fingers, what do you think? Sig figs? We're all kind of like in two, me too. 46 grams of solution. Again, you see where the explicit part comes in here? You can't just go grams, because grams are what? And things will cancel and be all confusing. Okay, this is an example where you have to clearly say, give enough information, grams of what. So let's work this problem. And a lot of times in chemistry problems, you'll find some kind of physical properties. In this case of nitric acid, you'll have the weight percent of nitric acid, weight percent of pure HNO3 in HNO3 solution, and you'll have the density. Okay, so those are going to be what I say tools to work the problem. On the next slide, I'm going to unpack it, but just here, okay, whenever you see 22.0%, you can go ahead and start writing it. 22.0 over 100. That's the parts per 100. In this case, it's 22.0 grams of pure HNO3 over 100 grams of HNO3 solution. How's that? It's watered down HNO3. That's kind of how that works. Now again, this is sometimes when you're working a problem like this, and you will have some of these to work over the weekend. Okay, the 1.3 grams per milliliter is the density, kind of throws people off a little bit. Do you think, I'm going to ask this, kind of throw it out there. Do you think that's grams of HNO3 per milliliter of HNO3, or do you think that's grams of HNO3 solution over 1 milliliter of HNO3 solution? And the answer, what do you think?
I think it should be the HNO3 solution.
It's the whole solution, yeah. Because you're not getting the component, you're taking the whole diluted solution. Exactly. And so here, that's an example. So if I unpack the density, that would be 1.13 grams of HNO3 solution over 1 milliliter of HNO3 solution. Explicit. Again, the reason we're explicit here is if we just put grams over milliliter, you're like, well, which grams does it? We're going to have to use both of these terms, grams of what? Okay, so that's how that works. So I haven't even looked at the question yet. But the question goes like, so those are my physical properties of HNO3. Here it says you need 75.0 grams of pure, out of the mixture, right? Pure HNO3. What volume must you use? So on the next slide, or a couple slides from here, you're going to see we always start with, to me, that's what we're going to start with. We're going to have a few arrows, and we're going to end up with, I'm going to just, I think, milliliters of solution. So sometimes when I don't know how to work a chemistry problem, I'll just kind of look at the physical properties, I'll kind of write down the units, I'll unpack them, and it's like playing puzzle. One of the things about puzzle is you can take the piece like this, and I guess in chemistry you don't really rotate at 90 degrees, but oftentimes you can rotate that puzzle piece at 180. Flip it. Okay? So here we go. This is unpacked, okay? Notice I just said here I left out the mixture. I described it just simply as solution, not HNO3 solution. So it's the same thing. Weight percent of 22.0 HNO3 percent. HNO3 means 22.0 grams of HNO3 per 100 grams of solution. And anytime you're dealing with the density, it's the whole solution. All right. So those are our puzzle pieces. We can use them like that, or we can flip them, yeah, at 90-degree angle or 270 decimal. So just starting down the road, I guess how we're going to do this. We can go from grams of HNO3 to grams of solution using the weight percent. And we can go from grams of solution then finally to volume of solution using the solution's density. So we'll put 75.0 grams of HNO3 over 1. And if I want grams of HNO3 to cancel, what units need to go at the bottom? Grams of HNO3. If I look back over at my puzzle pieces or whatever, you can see the weight percent had units of grams of HNO3. It's what I call the flipped version of the weight percent, though. Okay. So I put 100 grams of solution on the top, 22.0 grams of HNO3 on the bottom, units of 8 grams of HNO3 cancel. It's perfect. Now we're ready to go ahead and use density to get from grams of solution to milliliters of solution. If I want grams of solution to cancel, what units need to go in the denominator of the next term? Grams of solution, yep. So in this case, it's the flipped version again, isn't it, of density. Grams of solution will cancel if I put 1 milliliter of solution over 1.13 grams of solution. We just focus on the units. Our units are perfect. All right, get your fingers ready. We're multiplying and or dividing here, so we need to round according to sig figs. So how do we round our answer? Yep. It is 3. So 302 milliliters of solution. So it's a classic. Oh, anytime a teacher says it's a classic, or I see it as a classic, it's definitely a possibility you have a problem like that in your test. A good thing about y'all working your homework like you are is that it will sometimes you're just like, well, what's on your test? Well, kind of a lot of what I put on my. Speaking of homework, these will be due on Monday. Long week next week, guys. Sorry. We can do it. Now I want to go ahead and begin the next part. We definitely won't get through the whole next part. But who doesn't love the atoms? I know. So this will be the only bit of homework that's due. I love atoms. Oh my gosh. They are so adorable. Here you go. Maybe. There it goes. Oh. We're getting there. Okay. Okay. Atoms and their isotopes. Some of you guys know the way that gives us isotopes is we have a different number of neutrons in an atom, a particular element. But atoms, oh my. So we know we can split the atom, right? Here is, not split it. CHM fission. Yeah, they are kind of, with their nuclear testing and stuff like that. There's different ways to get energies out of an atom, and that is to split it or to fuse two atoms together to make something heavier. So we can split the atom, but we don't call that ordinary chemical reactions. That would be nuclear reactions. So if you're chopping away at matter, here in a minute you're going to see a pile of copper, like all copper atoms. You can't chop it. Once you have an isolated an atom, you can't make it any smaller. But that's some sort of nuclear reaction. We talked about this before. We said that in the whole hierarchy of matter, matter has mass and occupied space. It can either be a mixture or a pure substance. If it's a pure substance, it could either be an element or a compound. So over here, elements, like I said, we're going to pick on copper. If you look at a pile, if you look at copper metal in the lab or whatever, or copper wire in the wiring in this, okay, they're all just copper little atoms hanging out. Okay. All right, copper. Now, you might be curious, you're like, okay, so we'll go in biology lab and we'll use their microscopes, not telescopes, we'll use the microscopes to look closer and closer and closer at matter. Can we actually look at individual atoms? Not with those microscopes. But you can have fancy microscopes that have to do something funky with light coming from the atoms to actually kind of see these ridges are individual atoms. If I could animate this, which I don't think I can, I'll try. We got time. Did I hot link it? I don't think I did. Okay, but if I could animate this, this is maybe what an atom might would look like. So in the inside of the atom are can you see red and green? Okay, good. Those are protons and neutrons. And so what would this be outside the atom? Electrons, yeah. I say it's outside the atom, but it's still part of the atom. I should say it's outside the nucleus. Okay, it's like the outer part of the atom. So, yep, electrons. If I could animate it, they'd be like make it itch because they have a lot of energy, a lot of kinetic energy. That's kind of what gives the energy. So these are just some symbols of some elements. I'm kind of looking in my bag because I've got a slide here that you are going to have to memorize. Oh, memorize. I don't have to memorize much. But you are going to have to memorize some elements and their symbols. So these are symbols of the element. Like, well, those are just letters. Well, there are one or two letters that make up the symbol for the element. And if you have two letters, like Fe, the first letter is capital, the second letter is lowercase. Cobalt's important, for instance. Did I say this the other day? I don't know. It feels kind of familiar. But, of course, the symbol for cobalt is uppercase C, lowercase o, and you don't want to confuse that with carbon monoxide. They're two different things. So, it's important. Here's a figure from OpenStax from the textbook that just says kind of some random elements. So, like I think I started to say, you're going to have to memorize some elements. The thing you have to memorize is just the name and the symbol. So you don't have to memorize, like, on a periodic table, every element usually has two numbers. There's what we call the atomic number, which is the number of protons, and the decimal number, which is how much an atom of that type of element weighs, average atomic weight. So you have to memorize those numbers, but you do have to know the name and the symbol. So I kind of like, I like this because a lot of times students will say, iron, well, that's Fe, well, where did that come from? And usually the roots are Latin. So you probably already, well, you don't know this, but we actually, scientists, are getting heavier and heavier elements. So here's our periodic table over here. This is an old periodic table, and I think it's kind of fun. It has dates on it. And the dates are when it was discovered. The older I get, the more interested I am in history. Okay. There are some awesome periodic tables out there, and I'll try to bring in an app maybe Monday and kind of show you some of my favorite periodic tables. But yeah, they're amazing. What I started to say is, if you look at a periodic table, it's organized here by this red number. It's an increasing number. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it goes 11 through 18. We pick up 19. It goes across to 36. Okay, those increasing numbers are increasing the number of protons, okay, in the center or nucleus of an atom of that type of element. So to get heavier and heavier elements, all you got to do is bump up the protons. So here we go, 110 protons, 111 protons, 112 protons. This is a copyright 09, so this is what, 8 years old? Actually, within the last year, scientists have filled out this entire period called period 7. Here's the catch. Whenever you make these heavier guys, they're relatively unstable. So it's like playing a little game. Scientists have to basically smash smaller atoms together, increase the number of protons in the nucleus of that atom, and it has to live long enough to be dubbed an element. Okay? So sometimes students will be like, well, why would you even create something that was so unstable? You just never know. It might be the key to wormholes. Okay? So anyway, that's kind of how that works. So the sheet I gave you, or these red numbers. If you look at the sheet I gave you, what is find potassium. Okay? And the sheet I gave you, yep, potassium's over here in the first column. That 19 matches with this 19 matches with that little box. That 19 is the number of protons in the nucleus of an atom of potassium. So you have to memorize, you have to match the name and the symbol. For instance, 19, it falls between 1 and 20. So all of those first 20 elements, you got to memorize the name and the symbol. It's not too bad. Like, what's the symbol for aluminum?
AL.
AL, yeah. So, I mean, they're not, okay, let's do a hard one. What's the symbol for gold?
FE.
No, that's iron.
AU.
AU. I get AU and AG mixed up. AU is gold and AG is silver. Yep. So, you know. I mean, I say I get it mixed up, but if I concentrate, I got it. Okay, so those are the ones you're going to want to memorize. And, yeah, this is just a kind of fun little thing. Now, you guys, you guys all have your little, how far are your, so on your tests, this periodic table that's right here, okay, that is almost exactly, see, we've got all the period 7 elements. This is what you're going to get on your test. So what I might do, and actually this is the same periodic table you see other places, like I know it's in your lab manual, but you might want to take something like this and go ahead and mark those on here, just so you know, you're like, oh yeah, I know this is what okay? 92, what element's 92? Atomic number 92. Uranium, yep, uranium. Yep. Very good. So there are 7 elements, and this is kind of fun because we talked about this a little bit in general chemistry too. You know, if you go to a different planet, you'll be under different atmospheric conditions, temperature and pressure. And these 7 elements that are diatomic on Earth's pressures and temperatures may not be diatomic. So there are 7 elements that actually like to have another atom of its same sort together. They're always go in pairs. They're diatomic elements. And for that reason, we do a little subscript of number 2 and make a little formula to show the molecule. So here are the 7 diatomic elements. These are listed by increasing atomic number. Now, I'll tell you the way, years ago, the way I memorized this is by the German name Hofbernickel. I don't know. So if you spell out Hofbernickel, then you actually, I don't know if it looks like Hofbernickel to you, but it does to me. You have the 7 diatomic elements. So if I put a little subscript 2 here, we have hydrogen is a diatomic, oxygen's a diatomic, fluorine, bromine, nitrogen, iodine, and chlorine. They're all diatomic elements. I'm going to show you here the periodic table, and you're going to see that actually they're all kind of grouped over there. Okay? So So here they are. Here's your 7 diatomic elements, all kind of clustered. Some of you guys maybe remember this, but as the periodic table was arranged the way it is, the law of periodicity sort of, actually as you go up and down a column, we call these groups, and these have similar properties. So with regard to diatomic elements, I mean, you got your fluorine, chlorine, bromine, and iodine, they're all diatomic elements. Oxygen, nitrogen, and hydrogen. So the way this works is they didn't always understand the concept of an atom. Now, Dalton wasn't the first to come up with the concept of an atom. Oh my gosh, it was in the BCs. I think it was Aristotle or some philosopher came up with this idea that all matter is made up of little pieces. These little pieces are called atoms. So Dalton's atomic theory has some elements to it. So he was kind of the first chemistry sort of person who started to kind of come up with what is an atom and what would the properties be. So he said that all matter is made up of atoms, just like I think it was Aristotle, one of the other Greek philosophers. Anyway, this blue here means that this is part of his original statement, but it's not entirely correct. Because what did I just talk about? I talked about nuclear fission, which actually you can destroy an atom, sad face, and liberate a lot of energy at the same time. Okay. So we have another piece that's blue. Dalton originally said that atoms of the same element are identical. Makes sense. But they're identical both in chemical properties, which is true, but they aren't all identical with regard to the mass of all atoms. Not all copper atoms weigh the same. And this gets into the concept of isotopes. We'll be talking about that. It goes on to say, which is correct, that atoms of different elements have different masses and different chemical properties. Does that make sense? Aluminum is different than oxygen, right? Dalton also said, see, he's a pretty smart dude. He said that compounds actually are made up of atoms of different elements, okay? And that these compounds then would have discrete sort of ratios that these atoms would be combined to make these compounds. So, for instance, water has 2 hydrogens and 1 oxygen. This last statement of Dalton's original theory, atomic theory, I actually added to make it correct in red there. So he said it kind of goes back again to the nuclear fission sort of thing. Atoms are neither created nor destroyed. You can go ahead and make that a true statement if you say, as long as your processes are ordinary chemical properties, okay, instead of nuclear reactions. In science, in life, there's a lot of conservations of. You only have so much energy to go around. That's the theory of conservation, or it's not theory, the reality of the conservation of energy. There's this reality of the conservation of matter. Atoms you start with in chemical reactions in the chemistry lab or in the problems you're working are going to be the atoms that you end with. No alchemy here, right? Right? Whatever mass you start with is going to be reflected in the mass of your products. Now, I would say that some of you guys know Einstein. Is that right? Oh my gosh, are you serious? Is it a big E? Oh my gosh, I think it's a big E. E is equal to mc squared. And Einstein actually says, and this again is nuclear reactions, you can convert a little bit of mass to a lot of energy, okay, if you're doing a nuclear reaction. We're going to talk about this semester. So it can be converted back. So here's a figure from OpenStax. You gotta love them, right? You know, we said that mass cannot be created or destroyed. These next couple of figures just say that, for instance, if you're going to go ahead and make beer, you have your pre-beer and your sugar. Well, after your chemical reaction occurs, actually it should be hopefully nice and carbonated, okay? And maybe even sweetened along the way. Beer doesn't get sweetened, but so the mass of your product should be equal to the mass of what you start with. That's all it is. Like, how clever. They just thought it'd get our attention putting a beer bottle up there. This is similar in your car batteries. They don't last forever, do they? And actually, so